Hello students, in this video let us find the number of different perfect matchings in KNN. So what is KNN? KNN is a complete bipartite graph. So now in this video we are going to find the number of different perfect matchings in KNN. So what is the possible number of perfect matchings in KNN is what we are going to find. So let us consider one example here. So let n be equal to 5. So the example, the value of n is equal to 5. So the complete bipartite graph will be K5, 5. That means one of the partite sets will have 5 vertices and the other partite set will also have 5 vertices. So V1 and V2 are the two partite sets and each are having 5 vertices, and it is said to be complete because if we take a vertex from one of the partite set, it will be adjacent to all the vertices of the other partite sets. So for example, U1 is adjacent to V1, V2, V3, V4 and V5. Similarly, if we take another vertex U2, it will also be adjacent to all the other vertices. So this is called a complete bipartite graph. Now we shall find the number of different perfect matchings for this complete bipartite graph. So first let us write the bipartition of Kn, n. So let the bipartition of Kn, n be the sets V1, V2. So V1 will be equal to one of the partite sets. So let its elements be U1, U2, etc. like that, because we have n vertices, so we can have it to be Un. And let the other partite set be V2, which is equal to V1, V2, etc. up to Vn, because the other one also has n vertices. So these are the two partite sets of the complete bipartite graph Kn, n. Now we note that any matching if we consider any matching of Kn, n, we see that M will saturate, so that M saturates all the vertices of V1, and if it is so, then that will be a perfect matching. So that will be a perfect matching. So we note that any matching of Kn, n that saturates all the vertices of one of the partite set, then it will be a perfect matching. It can be either V1 or V2, whichever we consider, because we know that if we select one vertex from one of the partite set, it will be adjacent to all the other vertices of the other set. So for any matching of Kn, n to be a perfect matching, it is enough that if it saturates all the vertices of one of the partite sets. So that is if we prove that is enough, so that will give us a perfect matching. Now the vertex U1, suppose if we consider the vertex U1, it can be saturated. So this vertex U1 can be saturated in how many ways? Now U1 is adjacent to all the n vertices of V2, because it is a complete bipartite graph. So U1, if we consider, it will be adjacent to all the n vertices of V2. So it can be saturated in n ways, because it is adjacent to n vertices of the other bipartite graph. So what will be that set now? By choosing any one of the edges U1, V1, either it can be this edge or U1, V2 or U1, V3, etc. like that, U1, Vn. So any one of the edge we can have. So the vertex U1 can be saturated in how many ways? N ways. So this is the number of n ways in which the vertex U1 can be saturated. And this can be done by choosing any one. So by choosing any one edge from these n edges, the vertex u1 can be saturated. Then what is, then we will go to the next vertex, so u2. So now this can be saturated in how many ways? Now already u1 has been saturated, can be saturated in n ways. So u2 can be saturated in n minus 1 ways, because now u2, if we see, it is adjacent to n vertices of the other partite set, but already any one edge from u1 v1 u2 u1 v2 u1 v3 would have been in the set already. Then if we can't consider that edge, because it will be adjacent to the another like for example, if we take v1 u2, this is adjacent to u1 v1. So we have to leave one vertex and consider the remaining vertex. Though u2 is adjacent to n vertices, already one vertex will be adjacent with the previous vertex. So because of that, if both are adjacent edges, so it cannot be put into a matching set, in the same matching set. In that case, we should leave this vertex v1, and so the remaining vertex only we should consider. So remaining how many vertices we have? N minus 1 vertices. So therefore u2 can be saturated in n minus 1 ways. So like this, if we keep on going, like for example, the vertex u3 can be saturated in n minus 2 ways, because now the two vertices which are adjacent to u1 and u2 must be left, and we should consider the remaining vertices. So out of the n vertices, two vertices which are adjacent to u1 and u2 we have to leave, so it will become n minus 2 ways. So likewise, if we consider any vertex ui, it can be saturated in n minus I minus 1 ways. So that will be actually n minus I plus 1 ways. So this is for any vertex I. So then any vertex ui plus 1, it can be saturated in n minus I ways. So like this, if we keep on doing, we can find that the number of different perfect matchings, so the number of different perfect matchings in k n comma n will be equal to, so the vertex u1 can be done in n ways, vertex u2 can be done in n minus 1 ways, vertex u3 can be done in n minus 2 ways. Like that, if we keep on doing, it will be 3 into 2 into 1. So this will be equal to n factorial. So therefore, the number of different perfect matchings in k n comma n is n factorial. So we can just check out this with the help of the example that we have considered. So we have considered the example of k5 comma 5. So the vertex v1 can be saturated with how many vertices? There are n vertices in the other set. So it can be saturated with n number of vertices. So that n is here equal to 5, no? So this can be saturated with the help of 5 vertices. Now u2, if we take, already the vertex v1 which is adjacent to u1 has to be left behind. So after leaving it, the remaining vertices that it is adjacent to are v2, u3, v3, v4, v5. So these 4 vertices are the vertices which can be used. So the vertex the vertex u2 can be saturated in how many ways? Then it can be saturated in 4 ways. So remaining again, the vertex u3 can be saturated in 3 ways, vertex u4 can be saturated in 2 ways, and vertex u5 can be saturated in 1 way. So therefore the number of ways of saturating these vertices will be in k55 will be equal to 5 into 4 into 3 into 2 into 1. So when we multiply all this, we will be getting 5 factorial. So therefore, this can be done in 5 factorial ways. So therefore, the number of different perfect matchings in K5 comma 5 will be equal to 5 factorial. So this is how we have got this n factorial here. Hope you have understood this concept. It's a very significant problem in the examination point of view. Thank you.